tomorrow I think it's going to be the thing to do with everyone to say, do you know which day it is? But so it's a bit of a special session today. And Mike, are we live now? I was just chatting to be sure we were live, so so that you know all GCCA sessions are streamed live, but also recorded. So even if we don't have so many people here, we have some more people live, but also we see from the other events that people are checking afterwards and listening to what is interesting. So keep the energy. You will be listened to even if you don't feel you're listened now. So I'm going to try to set the scene, explain what recarbonation is, and also outline the methodology that was developed to quantify recarbonation in line with IPCC guidelines. And then we have the great honor to have two speakers from two countries that actually have just finished release work with country, at country level, to apply the methodology according to two of the methods. So, and the results have been released a few months ago in the UK and very recently for Brazil. So we're going to present this. And then we are going to discuss with you, Jonas, Bellona Europe, a bit more the enhanced potential and how concrete can then, how that potential to reabsorb CO2 can be enhanced and be actually a way to use the CO2 and store it, in fact, through usage. And then if we have time and if people have questions, then we will go into questions. So just to say, and it's not the same representation of the roadmap, just to change a little bit the way we present it, it shows the weight of each of the levers of the GCCA roadmap. And you see that recarbonation counts for 6% of the reduction, but it's really important, and we will get into the details of it. This is only natural recarbonation. So this is really a very conservative assumption of what happens during the use phase of our product. So it's even not what then can come from enhancing. So it means that if we were able to enhance more this potential, we could then maybe use a little bit less of the other levers. But I also think that part of the 36% of CCS, some will have to go as a use in the value chain and not be stored, because in all our carbon capture event, we heard that a lot is actually, or many plants will actually not have the storage. Now, carbonation, recarbonation, the terms are used interchangeably, but what we really have to understand here is that what we are talking about is the reversal of the emission of our process emission. So when limestone is heated, CO2 is released. This is the famous process emission about which we always speak in our industry. So 2/3 of our emission are the so-called process emission. This is a process that is energy intensive, and I'm a chemist, and I like to tell people that what is difficult in one direction in a chemical reaction, and it's difficult to decarbonate clinker, you need a lot of energy, it goes easily back the other way around. So it's the reverse of the reaction that we are provoking in our kiln, and it happens naturally. It is slow, but it happens naturally. You don't need energy, you don't need high pressure, you don't need anything. The concrete reabsorbs what it has emitted. And therefore, concrete provides a permanent carbon sink, and what we will show here is that this has been scientifically well established, and it's actually mentioned, we could say recognized in the latest IPCC report. So the sixth assessment report refers to sink associated with cement carbonation. So it's referred to, but there is no method provided by IPCC to quantify it. But there is room in country inventories. If you are interested, that's something we can share. Where is the exact reference? But IPCC inventories are about emissions and removals, and the removal of CO2 from the atmosphere by concrete is actually in the IPCC report. But this is all the natural thing, but actually we can enhance that potential, and we can manufacture artificial aggregates. There are companies doing now concrete curing. Carbon Cure, for example, is an example. There are many other examples. And then the carbonation of the recycled concrete. So when at the end of the life we crush the concrete and enhance this recarbonation. Now, there are many factors that will affect the carbonation or the recarbonation potential. It depends, of course, of the concrete characteristics, the concrete exposure conditions, low strength products, so the wall of mortar will actually carbonate rapidly and more. Actually, it's important to highlight that this phenomenon is known since since decades, and it's actually something that structural engineers have been fighting, because carbonation was actually what was creating problems with the steel reinforcement and corrosion of steel reinforcement. So really, again, concrete has been designed not to carbonate too much when it comes to reinforced concrete, but still the surface is recarbonating, and then, as I said, at the end of life, crushed concrete recarbonates more. Now, well known, it's already now a decade, I would say. It's in the EPD, I think, Miguel, it's since many years. It's in the EPD Environmental Product Declaration, product category rule tool, where it's quantified. And then also there is a large amount of international research and publication around recarbonation. And the one that are here are actually the one that served and that were used by IVL, which is a Swedish institute, to develop the famous IVL methodology to quantify recarbonation. And IVL has therefore worked on the basis of established research, looked at all what was available, of course the reference in the IPCC document, the standard that was existing with the PCR, the product category rule for cement and concrete, and has developed fully in line with IPCC methodology, a 3-tier methodology, in fact. And the way, I guess many of you are familiar with IPCC ways of quantifying emissions and removals. If you don't have much information, you go for a tier 1 assessment, which is actually then a very conservative assessment. So if you are quantifying emission, you would probably tend to overestimate the emission with a tier 1 methodology. If you are quantifying removals with a tier 1 methodology, would actually underestimate the removals. So this is the conservative way. And then if you move to a tier 2 methodology, you need more data, because you need to substantiate more your claims or your emissions, or substantiate more your claims for removals. And then you can even go down to a tier 3 methodology. And so we have now this 3 tiers methodology that has been developed and tested against as well all the research that was available, and actually it accounts for, even the tier 1 accounts for the use phase. The end use phase is the secondary use phase, and the use phase, as be shown, is 20%. Now, 20% of the process emissions, right? So here, the combustion emission, they are out of the equation. So the 20% that are claimed is 20% of process emissions. So it's not 20% of the total. That's also the way IPCC accounts for things, and that's the way we also have to express it that way. But we are always very clear about it. And then a bit can be used because of end use, so the demolition, the crushing, the stockpiling, wherever in the world. This is, again, the conservative assumption, and then secondary use. And then there is also an adjustment that is foreseen for mortar, even in the tier 1. You may have seen, for the one who are used to it, you may have seen many Chinese studies, for example, that claim a much higher recarbonation potential than the 20% And this is, I mean, there are different reasons for it, and those studies were considered here. But one of the main reasons for the difference is a much higher mortar assumption in China than elsewhere in the world. So that's the reason for the difference. But this is what can be claimed, I would say, or assessed. So very conservative assumption. And then we have a tier 2 and tier 3. And I think I won't give too much explanation about tier 2 because that's actually what has been tested in the UK. So I think without further ado, I will pass on to Miguel Angel of IECA. Miguel Angel, you can maybe say a few words about who IECA is as well, and then you can take us, you can come here to speak. I think that's good. And then you can take us through a tier 1 model. Thank you.
Thank you. Claude, a little bit more about the tier 1. And I will also apply this method to the Brazilian case. In Brazil, this is the reason because, well, tier 1, the special part, Brazil is a huge country and has 1991 cement factories of cement around mostly in the coast, and there are 23 companies managing these 1991 plants of cement. The peculiar case is that also the clinker factor is quite low. It's about 0.65 now and is expected to be about 0.6 by the end of this decade. Also, this country, as you can see here, the carbon dioxide emissions per ton of cement, not clinker, per cement or cementitious materials, is quite low compared to other well-developed countries. This is a particular case that is due to several reasons that are explained in a paper, an extended paper. Going back or going to the tier 1, as Claude said before, is the simplest method. Wait a moment. This is one slide. No, one is the light is missing. Okay, well, this is the simplest method, as we can see. Also is very conservative because only 20% of the calcination emissions are considered to be absorbed, uptake by the concrete or mortars. The equation is, as we can see, and also Claude explained before, that 20% of the calcination or the carbon dioxide emitted during the process are considered to be uptake. Then 2% of these emissions are uptake during the final of the service life of the structure, and finally 1% can be considered to be uptake in the secondary use. At the end of the day, this is 23% can be absorbed by the cement-based materials. All these, these equations are well discussed and presented in the publication, the IBL publication, and the reference is here in the slide. The schematic process is as follows. Here we can see that CO2 is absorbed following the fixed second law, the square root of the time. And after this first period, during the service life, we have a second and third period. We have 3% more of uptaking due to the final use and secondary use. The good news is that this method is very easy and is feasible for all the countries. And all the countries can prepare and can estimate, can do this estimation quite easily. Well, The particular situation in Brazil and in many South American countries, Africa and China, as Claude said before, is that a lot of cement, quite amount of cement is used in mortar. It's a bag cement, and we can consider an additional factor. If the clinker use in mortars, in bag cement, is less than 10%, this value is considered to be 10. Then if we put here 10 minus 10, well, this is 0. This factor is not considered. But if this factor, well, if the consumption is higher than 30%, then we consider to be this factor directly 30. 30 minus 10, we have 10. Sorry, we have 20. Then, if we are between 10 and 30, we consider exactly the value, well, more or less, because this is an estimation, a rough estimation. We consider the consumption of mortar, of clinker to be used in mortar. This is one particular case. And now the results in Brazil, as an example, are as follows. We have here the clinker production. As we can see, this clinker production, the cement production, follow the economical situation in the country. We have a good period, we have a crisis, we have a good period, we have a crisis. The carbon dioxide emissions also follow the same trend as expected. Also, we should take into account the imported and exported cement. Why? Because we consider the uptake, the absorption in the country. Then we should sum the imported cement, the imported clinker, and we should subtract the exported clinker and cement. Also, we can recognize the good periods and bad periods, economically good and bad periods. As we can see here, in a good period, Brazil, as other countries, import cement. In a bad period, we can see here about 2005, the country export, you see, export and no import. Now, the conclusion, well, the final result and the conclusion is that following the production, the import and the export data, we have the carbon dioxide reached, well, the top was about 7,000 kilotons of carbon dioxide per year. But this is the maximum value reached about 2015. And the conclusion is that the carbon dioxide uptake in Brazil during 30 years, from 1990 to 2019, is about 140 million tons. This is quite a lot, and this is a very conservative method. If this country develop a tier 2, as then Diana will explain, probably this value could be a little bit higher. And also to remark that this tier 1 is very easy to use and is feasible for all the countries. And the recommendation is that all the countries use, at the beginning, use this methodology. Then I would like to say that the national carbon neutrality roadmaps should implement this part. In many countries, in many organizations, follow the 5 Cs method, and only to remind you that is composed of clinker, cement, concrete, construction and recarbonation. This final step should be considered also in all the roadmaps. This well, is a summary of this publication, and we expect to have a new publication by the end of this year. And finally, thank you for your attention.
Maybe just, if I may, one question, because I think it was really interesting what we saw, and I didn't say it in my introduction, but really we are also, and Sweden is reporting recarbonation. It's national inventory now as a footnote, which is IPCC compliant. And what is really interesting is that you see even at country level, so if a country wants to claim, okay, so much of my building stock recarbonates, it has to take into account the import and exports even for a tier one. And I think that was really interesting to see on the Brazilian case. It's the first time we see this impact as well on then, okay, you can't claim as much as what you have you think. So thank you. We will have a discussion afterwards, and I will immediately pass on to Diana. So it's going to be even more complex now, because now we move to a tier 2 methodology. Yeah, it's higher level, but it's...
Thanks, Claude. Thanks for inviting me along to speak about this work today. So I'm Diana Casey. I'm Executive Director for Cement and Lime and Energy and Climate Change at the Mineral Products Association, which is the UK National Trade Association for cement producers and concrete producers in the UK and a number of other mineral products. So, Claude talked about the process emissions, and that's what the calcination reaction is reabsorbing. In the UK, our emissions split is about 67% process emissions and 33% from the fuel. Just as a quick reminder then on the 3 tiers that the IVL methodology put forward. The tier 1, which Miguel's just presented on, are for use when you don't have, or you might have limited statistics on concrete use. The tier 2 goes a step further and requires information on where the concrete's used, and then it uses the standard, the EN 16757 methodology, along with some fixed uptake values for end of life and secondary life. And then the tier 3 goes even more advanced and needs kind of software models, 50 years worth of cement consumption data, detailed concrete use covering at least 3 years, and it also looks at carbonation of supplementary cementitious materials like slag and ash as well. So the UK project focused on this tier 2 model. And we, as MPA, so as the sector association, we actually led this work with some funding that was provided by the UK government. We worked with Ricardo, who are a consultancy, and they actually produced the UK inventory every year, so they were really good people to partner with. We also had a number of other kind of subcontractors, Heriot-Watt University, Leading Edge, and the Concrete Society. So in terms of the model development, we started off with a literature review, and this was done by Dr. Phil Renforth at Heriot-Watt University. As well as doing the literature review, we also did a review of the data sources that we have that we could input into this. Just going on the literature review to start with, it concluded that the IVL Tier 2 methodology, based on the standard EN 16757, would provide a robust method for calculating CO2 uptake due to carbonation of concrete. But it did find that it sort of fell short on the end of life and secondary use of concrete. We didn't think that that was going to be suitable for a UK specific model. So this whole tier 2 model is very UK specific. It's using UK data to work out what the recarbonation is in the UK. So it suggested that we ought to calculate our own kind of value for that kind of end of life part. The model itself, then we identified the annual activity data for a number of primary uses of concrete, and also what happens at the end of life and secondary use. We used those primary applications then to calculate an emission sink factor, and then we did the calculation for the end of life and secondary life as well. The model itself was then validated by comparing with experimental carbonation data. We also undertook an uncertainty analysis, which is required for the IPCC. And then we looked at providing some recommendations for future work to refine the model, but also for further research into carbonation. So I'm going to talk mostly today about the model itself. I'm going to start with a bit on the data though, and I do touch on the comparison with the experimental data because I think it's quite interesting to see. So our review of data sources in the UK found that we basically have two approaches to data. We've got the top-down data, so this is the production and the supply of cement and concrete at the national level, and then we've got the bottom-up data, which is the different types of construction where concrete is used. Now that bottom-up data, it may be cross-sectoral, covering the whole construction market, or it may be specific to an individual sector, such as housing or infrastructure. Where we found gaps, we got a consultant leading edge to undertake a market survey just to try and fill those gaps and provide a bit more information. Now, we had to work out how the concrete is used predominantly in the UK. So what we did was we came up with these 5 main primary use applications, and this was based on expert opinion and the market survey as well. These 5 primary uses in the UK cover about 80 to 90% of the UK cement market or UK concrete market. So we've got buildings of steel composite frame construction types, so these are things like offices and other commercial buildings. We had buildings of concrete frame construction types, so for example high-rise residential. We had buildings of masonry construction types, that's low-rise residential. We had infrastructure projects, and then we had another category for the mortar and the merchant sales of bagged cement. So for each of these applications, we took a typical UK-specific prototype and we calculated a CO2 emission sink factor using the 16757 method, which I'm going to go through in a second. Once we'd done that, we had to then make some adjustments to make sure that the annual distribution of concrete between the applications was consistent with the top-down data from the production. It was all summed together to give us an overall emission sink factor at the end of the project. So this summarises the methodology for calculating the emission factor in EN 16757. So to calculate the uptake, you start with the maximum theoretical carbonation of a CEM1 cement with a 95% clinker content. So that's 0.49 kilograms of CO2 per kilogram of cement. We then multiply that by the depth of carbonation. So this is kind of how far into the concrete the carbonation has moved. And that's been found through testing concrete samples. And Miguel mentioned that increases with the square root of time. We also multiply by the degree of carbonation. So this is a measure of how fully the concrete has carbonated within the carbonation front. Now we know we don't get a full conversion of calcium silicates and oxides to calcium carbonate. So that degree of carbonation gives the proportion of the material that is carbonated. The EN 16757 standard actually sets out a range of factors for that degree of carbonation for different concrete strengths and different exposure conditions. So combining all of that together along with the quantity of the CEM1 in your concrete, you can work out the emissions factor. I mentioned Tier 3 starts talking about the carbonation of SCMs, but we know that the inclusion of supplementary cementitious materials in the concrete does accelerate the carbonation a bit, and there's a slight adjustment to the formula to take account of that. I'm not going to go through every primary use application because we'll be here all day. So I've just chosen 2, partly because they're linked as well. So I've taken the masonry example. So this is a mid-terrace house. And then I talk a bit about the mortar. So the prototype we used for the masonry one was an 80-metre squared, 2-bedroom, 2-storey mid-terrace house with masonry construction. It has a pitched roof and concrete roof tiles. So the emission factor calculation considers the carbonation of concrete in the foundations, both the strip foundations and the foundation blocks, the ground floor beam, the party walls, the external walls and the roof tiles. So these are all the different elements that we had to calculate the carbonation for. So for the lightweight aggregate blocks that are in the external and party walls and the concrete roof tiles, the carbonation front will have progressed through the full depth of those blocks or tiles by the end of the building service life. And that, when you put all of that together, we find that the CEM1 content of the masonry building is about 136 kilograms of CEM1 per metre cubed of concrete, and the emission sink factor comes out at 18.6. Now, the mortar that's used in that building wasn't included in that calculation because it was included in the other one, which is the link, so in the mortar and kind of bagged products. So in that case, we base the mortar use within the masonry house prototype for the party walls, which we assume to be concrete block construction, and then the external cavity walls, which are block and brick. And again, we assume that the carbonation front will have passed completely through the full depth of the mortar over the course of the building service life. And in this case, we found the CEM1 content to be 199 kilograms of CEM1 per metres cubed of concrete, and we have that higher emission sink factor of 43.93. So we did that process for all the other three primary use applications as well. And once we'd got those values, the emission sink factors, we compared with this experimental data. So these images show freshly cut concrete cubes. And we've applied a phenolphthalein indicator, which will become colourless at lower pH. So the bits around the outside where there is no pink colour, those are the areas that have been carbonated. And the pink area is the bit that hasn't been carbonated yet. And we're quite lucky in the UK. Dundee University has samples at 18 years old, so they've been curing for a little while. And the Building Research Establishment has some that are 2 years old. And we were able to test these to check what the carbonation is. And what we found was that the results showed that for normal strength concrete, so less than or equal to 40 megapascals, there was very good agreement between the methodology in the EN 16757 and the cubes that we tested. However, for higher strength concrete, so strengths greater than 45 megapascals, we actually found the results were slightly less consistent, and that was one of the recommendations we then had later on, was to do a bit more work around those higher strength concretes. So very quickly, the end of life and secondary use. We took, to calculate this for a UK specific factor, we took UK construction and demolition waste statistics. We found that the concrete fraction is around about 59%. We then worked out how much of that waste was from what type of concrete, so we could work out the strength and therefore work out how fully it would have carbonated, etc. And we came up with this result of 39.41 kilograms of CO2 per metre cubed of waste concrete for the emission factor, which equates to 21.39 kilograms of CO2 per tonne of concrete. So I haven't gone through all the uncertainty analysis, because that's probably a whole other 3-hour session on its own. But in terms of the results, we found that in 2020, the model came up with, for the UK, an emission factor of 1.548 million tonnes of CO2, plus or minus 34%, as the contribution of concrete as a sink in the UK for that single year. So that's equivalent to about 0.4% of UK greenhouse gas emissions and 31% of the calcination emissions from UK cement consumption. So the project report containing all this and a lot more information has been published, and we are under discussion with the UK government now about getting it included in our inventory. Thank you.
Thank you, Diana. Thank you so much. And we can go for immediate question before you speak.
Thank you, Jonas Helseth from Bellona. The 31% from consumption and it's 40% from production. Could you explain that? I'm not sure if I caught what you meant there.
Yeah, this is the, so the cement consumed in the UK, we have about, well, at the moment it's about 30% of imports. So we've calculated the carbonation for all the cement consumed, and then we made an adjustment to work out what that means in terms of just the cement produced, where we're actually making the process emissions in the first place within our boundary. But I think really you need to include it in terms of the whole, all the cement you're consuming, which includes the imports.
I guess that might be a question between countries, as who can claim the sink. That's an important question. I think that from a cement industry perspective, or it's clinker that recarbonates. So that's why we have considered that we could include it in our roadmap, because it's the clinker that reabsorbs. So and that's the whole logic, is to say the natural part is related to clinker produced. But I think it will be an interesting question when more countries will start to report the recarbonation in their inventories, and this is also why I highlighted for Brazil that correction. If I mean, because I've been following this work a bit more involved at the beginning than now, but I'm quite proud of what our industry is doing to really quantify this potential. So thank you, Diana. And I don't think you have slides. You're a no slide man. But the floor is yours. Yeah, you can stand there, yeah.
Thank you, and thanks for the kind invitation, Claude. I'm very happy to be here. So, Jonas Helseth from the Bellona Foundation, international environmental NGO. We work a lot on industry. I'm heading the EU work of Bellona, and industry has been the main focus area for many years. We also work a lot in member states of the EU, also in the UK. Haven't been much in Brazil lately, but we used to work actually with Camargo Correa in the past on cement and decarbonization. So very good to also hear on the work you're doing there. I'm going to talk a little bit about use of CO2 in the context of cement and concrete, and it's a topic that I spent a lot more time working on the last, say, 6-7 years than I would have wanted to. And maybe that's not a nice thing to say, but it's true, because I think that the European conversation about use of CO2 hasn't always been helpful, and the context of concrete and recarbonation, or carbonation, you say, it's sometimes used interchangeably. I think that's not been helpful either, but that in a way has been on the sidelines of that conversation, and that's been, I think, very unfortunate. It's been unfortunate for getting policy making that actually works for recarbonation, and it's been unfortunate for getting the carbon accounting right around these things, because that's what we've been doing a lot of work on, is carbon accounting. How do you follow the carbon, in particular in the context of capturing CO2? How do you make sure that there's a liability, there's a clearly placed liability? How do you ensure monitoring on the different processes? And this is something that has become extremely complex, and there is too little expertise around to make sure these things are done right. So a lot of the conversation happens on claims, and claims are sometimes based on data, based on numbers, sometimes not. So I think you show the number of 23% for the recarbonation, but I've seen claims from some cement companies around the world of 40%. And these are claims that I would like to see more data for, because I think transparency is key here. If we're going to work on a functional regulatory framework for incentivizing good solutions, we need to have data, and we need to have transparency. And we need to have also, of course, a lot of independent research going into this. And it's been too little of that. So I'm also very happy that you at GCCA are working on this and providing data and helping that conversation. In Europe, it's been confused. So just a little bit more background on why I'm saying that before I get into the actual topic here. The discussion around CCU, or utilization of CO2, in European countries and Brussels has been very much focused on only one thing, which is what is now generally referred to as e-fuels, or electrofuels. In the past, used to be referred to as synthetic fuels, sometimes referred to as Wunder diesel, and things like that. This is something that happened and pulled a lot of industries, including the cement industry in Europe, into that conversation because of political incentives, because of economic incentives, with the Renewable Energy Directive that wanted to drive the uptake of such fuels. But that led to a conversation which should have been about things like, to my mind, recarbonation, led to that being about something completely different. And in fact, it got so messy that you had a lot of the European industry, including some cement companies, pushing for electrofuels with CO2 from cement, that should be treated in the same way as, for instance, recarbonation. Which means if you take the assumption that recarbonation is a permanent binding of CO2, or at least a very long-term binding of CO2, you want to treat that in the same way as putting CO2 into fuel, which is obviously going to be, combusted and therefore emitted instantly at, I would say, maximum half a year after production. Then you end up with a carbon counting that doesn't make sense, and you end up with an incentive scheme that doesn't help the stuff that we need. So that's been our starting point for this, and that's why we've also been trying to engage, and I think we successfully engaged the European cement industry in turning that debate. Now, some of you might know that the European Commission is going to very soon publish a methodology for what type of uses of CO2 could exempt industry from surrendering emission allowances, meaning treating that as a permanent abatement. And I think we can say with confidence that recarbonation is going to be on the right side of that conversation, whereas fuels are not going to be on the inside of that methodology. And that's a good thing, but it's been taking 6 years of a conversation that's been all over the place. So I'm glad we're now focusing on this here. And for us, I think we've been very clear as an NGO that there should be a benefit to recarbonation, or enhanced carbonation, as we usually refer to it. There should be a benefit for that, and I think we can also refer to it for the purpose of climate action conversations as permanent. It doesn't mean that it's permanent per definition, but for the purpose of stopping CO2 from reaching the atmosphere and contributing to climate disaster in the next decades, it makes sense. Of course, we need to ensure that the monitoring is in place, and we need to make sure that when there's a demolition, that no one gets the idea to recalcinate the demolition waste and ruining the whole point. So the monitoring has to be in place. There has to be some criteria for how this is done, but I think there should be a benefit to this, and it should be treated as a real process. However, we need to, of course, make sure that the timeline is also done correctly. So, of course, when you produce cement, we have we have hundreds of millions of tons dumped in the atmosphere every year, and the recarbonation process, very different, is of course something that happens over a long time. But we need to think about how we get that benefit right, and I think it should be there. So we are, happy to also work with the industry to help get incentives in place, to help make sure that we have a methodology that incentivizes good practice in this space. So I guess one of the things that still is very important to underline is that the emissions are still real. So this cannot provide, an excuse for not addressing those. In some cases, if we get to zero emissions in the industry, there could be an additional benefit, and we can talk about that. But this cannot provide any excuse for not throwing everything we got at those hundreds of millions of tons of CO2 that we are currently, I'm not pointing fingers here, we collectively as humanity are dumping in the atmosphere from, for instance, cement industry. We are all using that. We're all using that concrete to build houses, to build bridges, to build wind turbines, to build, railways. We're all using that. We're all benefiting from it. So we all have a responsibility to think about how we get that done. And we had a good conversation yesterday, I think, in one of the official side events with Claude about how, the COP and the parties here and some of the finance people who are in the room here as well can help make that happen. There are some key pieces coming out of that conversation. We need to make sure that the cement industry around the world has access to infrastructure that can help decarbonize. And I'm thinking in particular about CO2 transport and storage infrastructure, which is distributed in an extremely inequitable way around the world. There are some areas where you have an oil and gas production where there is know-how, where there's infrastructure in place. Most of the cement production in the world doesn't have that. And if we just throw money at decarbonizing cement without making sure they have an equal distribution of infrastructure, we're going to create winners and losers that are essentially the same winners and losers we have today around the world, and that's not a fair way to deal with this. So I would like to also invite the industry to work with us on addressing that. We can work on methodology on permanence, we can work on incentives for this, but we also expect the industry to make all the efforts available and throw all the technology that we have today. We know how to get to zero emissions in cement. And we can have 100 excuses for why that didn't happen 10 years ago, because we knew then too. But there is no excuse that is good enough for that. We just need to find out how we get the money in the right place and how we create lead markets for decarbonized products so that this becomes a race to the top for the industry everywhere in the world. So I think I'll stop there. Thank you very much. Looking forward to any questions.
Thank you very much. And yes, if there are questions, Jonas? And I suggest we don't sit on a panel. It's such a nice room. No questions? Okay. I have, if I may, I have just, and I don't know if you have to rush to another event or not, but I don't want to make it too long. But you were commenting to me that you're thinking, because you have done this work for Brazil, but you are based in Spain, Miguel Angel. And what are the challenges to implement the Tier 2 methodology in a country like Spain?
What is quite difficult, because this well depends on the politicians, and the politicians today think one thing and tomorrow the opposite one. We went to the official how do you say, the climatic change office in Spain 5 years ago with the Tier 1. We'll explain the Tier 2, and we can develop a joint venture as UK has presented right now, and they then attended our claim. But last year, the same people came to us saying that, well, tell me something about that, presenting me the estimations, because right now it's quite difficult that Spain can comply with the compromise. It's quite almost impossible to reach in the 2030 all the reduction of CO2 globally in Spain. And in my personal opinion, probably they want to try to take a little bit CO2 from here and there, and now they are a little bit interested, but only a little bit.
Okay, so I think one question we get often from, and that will be a bit my concluding remark, because this is just not greenwashing, this is happening, and if a country includes recarbonation in its inventory, and maybe that's important to highlight, it's also then included for the reference year, right? So it's not that you start to include now, so it won't all of a sudden bring a super reduction. Everything is rebased, of course, so because some people do tend to think, oh, you are including recarbonation from now, so it's just to get some additional benefit, but it doesn't bring additional benefit, right? Because you have also to include it then in your 1990 baseline, right? So I think that's an important clarification, because I don't want your comment to be misunderstood. It's not that all of a sudden we have invented a way to absorb some more CO2. I think, thank you, Jonas, for, oh, yes, sorry.
So, thank you. I'm Nils Røkke from SINTEF, a research institute in Norway. I'm just wondering about what kind of amounts are we talking about per year for the global cement industry? I'm not sure if you showed that, you know.
I think.
Oh, there it is, right.
It's there.
Yeah, so it's 240 million tons.
Yeah, so it's 240 million tons, yes.
Right, okay. And is that?
Andrew will come.
Yep, so that's in 2050.
That's in 2050.
So the figure today is a little bit higher. A little bit higher.
Right. But is this accounted for in the models they're running, for instance, on climate? Because I was kind of thinking, that we may be getting it wrong on the climate sensitivity, actually. The climate sensitivity. I mean, the doubling of CO2 and what temperature increase you would get. You know, if that is not taken into account, we could get it wrong. Although it's it's probably too small as probably in the error band. But anyway.
It's 6%. It's 6% of the 7%. We're 7% as a cement industry, and that's 6% of the 7%.
Yeah, but the question is what's the impact of climate change on the recarbonation?
Oh no, that wasn't the question. But you're right. There's two questions. One is how significant is the 6% of the 7% to the 1.5 degree warming, and how and I think it's within the error band, to be honest. The other question, Claude, you're absolutely right, is if the CO2 concentration is going to go up by 2050, the rate of recarbonation will accelerate, and we haven't taken that into account in that 6%. Maybe that would go up to 6.6. I think once again it's probably within the error.
So, Mike, no question online, I guess? No? So, it's just important to ask. There might be someone willing to ask a question since a long time. I think that if everyone agrees, I will conclude this meeting. It was not as crowded as our other events. Our next event is tomorrow at 9. We're going back to carbon capture, use and storage, and we are on the enabling policies. So there's not going to be that much recarbonation. But thank you very much for your interest in the topic. And you have also our whole program, our events. You can either scan it or get a copy. So thank you again. Thank you to our speakers.